and use those as part of your writing process. So for the next 2 weeks, we're going to, we've already covered a little bit of OOP. We've covered the more practical aspects so far of objects and classes in Java. But now we're going to look at OOP in a more broad context, in a much more abstract way. Because Java is not the only object-oriented programming language. In fact, there are many object-oriented programming languages. And even if a language is not object-oriented, it probably still has a concept similar to some of the aspects of object-oriented programming. I don't want to get into a history because it's not a history class. But just know I do want to give it my perspective on the history. Obviously, computers didn't start out with object-oriented programming. The very earliest computers you actually programmed in binary using punch cards. They were mechanical computers that you punched through a punch card for 0, or maybe it was a 1, I forget, and then you didn't punch it for the other one, so maybe a 1 that way. And you were forced to be the compiler. So if you had an idea of an algorithm, you had to write it out on a blackboard, then translate that to the actual machine code and punch your cards and make sure that you didn't get one bit wrong because there's no debugger, right? Well, that was terrible. That's not a proper way of, I mean, it was all you had back then. We're talking about the 40s, 50s here. It's all you had back then. So along came assembly. Assembly where you could write it in machine instructions like load the value 5 into register 6. Then add whatever the contents of register 6 to register 7 and put the result into register 8, right? You could do things like that with assembly code. But of course, it still forces you to think like a machine because it forces you to think in terms of memory addresses, in terms of registers and loading things from memory and stuff like that. So along came C, one of the first high-level programming languages that was intended to compile to assembly code and then from assembly code into machine code. Right? Where each step of that evolution, you are taking a step further away from the actual machine and a step towards natural language, right? The Star Trek ideal of you can tell the computer, this is what I want you to do. And there's no ambiguity, and the computer suddenly understands it, right? We're still way far out in the future to get that kind of programming. The best programming language is English, right? Or if you speak another language, then a natural language, right? We're still walking towards that direction. In the 80s, you started having object-oriented programming languages. C++, Objective-C, those were born very early in the 80s as extensions to C that also had these objects, because you didn't want to. If you're still in C land, right? You're still talking about things in terms of numbers, integers, doubles. Characters, even though you have a collection of characters, you have a string, that you still don't have that concept in C because you have an array of characters with a null terminating character at the end. It still forces you to think more like a computer than like a human, the human that you are. And so along comes object-oriented programming to give you a more human-like experience. Rather than speaking in terms of pure numbers and variables, now you can start talking in terms of objects. A student object that represents a real-world student, a game object that represents a real-world game, or a publisher object that represents a real-world publisher. Right? Now you can start. Now you don't have to think in just terms of numbers and low-level kind of stuff. You can start abstracting it away and start thinking about these connections to real-world objects. The bank account and the customer. How do they interact? What's their relationship to each other? You can start talking about those higher level abstractions. And so that's the very brief history of OOP that I don't want to get into. Of course, now most languages support some or all aspects of object-oriented programming. Java was conceived first as an object-oriented programming language. It's still not a pure object-oriented programming language because a pure object-oriented programming language will look terrible. If you want to, go ahead and play around with a programming language that nobody's ever heard of called Eiffel. And that's a pure language, but nobody uses it. So I think is it Bjarne Stroustrup? I think the inventor or the developer of C++. I might be misattributing this, but he said that there are only two programming languages: the programming languages that everybody hates, and the programming languages that nobody uses, right? So you have evangelists that really love their programming language of choice, but it's a niche programming language that nobody ends up using. But anyway, that's the brief history of object-oriented programming. You've got a lot of object-oriented programming languages: C++, Objective-C, C#, or languages with OOP support that was added on later. For example, PHP. Classes were added in PHP 3 or 4, I forget. They were not part of the original PHP standard, but they were added later. JavaScript, it started out as an object-oriented programming language, but not in the traditional sense, because JavaScript doesn't have classes until 2 years ago when they started they added class support. And Python has classes as well, even though most people would call Python's lineage from Scheme or Lisp or whatever it came from, that it's more a functional programming language. Well, you still have objects in it, right? It facilitates the modeling of real-world entities, as I've already said. It emphasizes modularity and decomposition. That instead of taking a top level, a problem and breaking it up down into little parts, you actually start at the bottom and say, what do I need to represent this problem? Do I need a bank account object because I'm working with bank accounts? Do I need a student object because I'm working with an enrollment system? Once you've got those basic objects and the data representation, then you can start fitting them together like Lego pieces. That this one interacts with this one. And you start building up from the bottom up until you have solved the problem, unlike a top-down solution like you, say, might have done in C. There's a clear demarcation of responsibility and functionality. A student object is responsible for student things. A bank account object is responsible for bank account things. A game object is responsible for game things, right? Whatever that happens to be. And that's up to you as a designer to think, what does this object represent, and how should I model that real-world entity? You also have the concept of ADTs, abstract data types, which are more general mathematical concept. It's the theory that object-oriented programming is based on. We won't get into it, but if you're interested, you can take a hardcore programming language theory course. And as I said, many object-oriented programming languages out there, and even if they're were not originally OOP, they definitely have added OOP support later on. So what are our objects? Right? Again, that's a brief history. I don't want to belabor it anymore. Formally, an object is a general entity characterized by three things. There's this indent here, identity. Let's see if that indent's good. Identity. It's an aspect that distinguishes an object from all others. Right? So you need to have identity, that this student instance is distinct from that student instance over there. How do you achieve that? That depends on the language, right? I'm going to keep things a little bit abstract here until we have need of actually talking about Java, because different programming languages handle and implement object-oriented programming concepts in different ways. You note, for example, off the bat here, I'm calling them objects. In Java, we call those classes, right? Or the class is a blueprint for creating objects, and we call the objects actually instances. And there is an object class in Java. It's at the root of the hierarchy and everything, but it doesn't have to be that way. Again, like I said, JavaScript for the first 20 years of its existence, however old it is, was an object-oriented programming language, but it didn't have any classes. It was a prototype-based object-oriented programming language where you want an object, okay, go ahead and create one, right? No blueprint whatsoever. You want it to have this thing, okay, go ahead and throw it in there. It's now an empty bucket. You want it to have a variable called first name, go ahead and throw that in there. Now it has a first name. You want it to have a function that does something, go ahead and throw that function in there. It was prototype-based, where if you wanted to create a new object, you would actually prototype clone this object over here. But again, I want to drive home the point that not all OOP languages do the same thing, implement a concept in the same way. Right? I'm going to keep it as much as I can separate from Java. The second thing you have is state, which is a collection of properties, or sometimes they call them elements, attributes, data, or fields. Right? I think Java prefers to call them fields, member variables, fields in a class. And then finally, you have behavior. Right? It describes what an object does or how you can interact with it. And that's achieved generally through methods, functions, etc. that belong to the class. Right? How you end up using that object. So we've already really covered this in Java. You have member variables, state. You have member methods, the methods that you can put into a class. Those become part of the behavior of an object. Sometimes we call that the interface of the object. Because how do you use it? Well, you interface with it. You use its publicly available methods. Identity is simply an aspect that separates it from all other objects of its instance. And that could be the state, or it could be something else. Right? It could be a function that you call this. I've got this object and I've got this object. Are they equal to each other? Are they the same object? Well, you call a function on it, equals in Java, and it says, yes, they're the same thing for all intents and purposes. Or, no, they're not the same thing. Right? And so you can either do it through the state or through the behavior. Right? In object-oriented programming languages, communication and control flow with objects is done via what is called message sending. Right? We can, and basically this boils down to you've got methods in an object, you can call those methods, right? We can invoke a member method on an object, right? And basically you're calling a function. Well, that's like sending a message to that object that I want you to go ahead and run that method that belongs to you. And it's just another slightly different way of looking at things. I mean, if you've got a function in, say, C that doesn't belong to an object, it's not an object-oriented programming language, you're still kind of sending a message to the program to invoke and run that function. Instead, it's just from a different point of view. Instead of sending that message to, say, the program, we're sending it to a particular instance of an object. Right? Communication is facilitated with or by an object's interface. Right? These are the publicly available methods in an object. Right? You can have private methods, and we'll look at that later, but the private methods are not part of its interface because from the outside world, it's not visible. You can't see them. And if you can't see them, it's not part of the interface. It's part of the object, but it's not part of the outside world. You can't see it from the outside world. You can't invoke it, though, so it's not part of the interface. Another difference with traditional, say, structured programming language like C is that objects are constructed rather than assigned. Right? So, for example, built-in types like, say, int or double, right, are known to the language and the compiler, and it knows, I'll put that into quotes there, it knows how to build and assign a value, right? And what do I mean by that? Is if I go int a is equal to 42, well, a computer doesn't understand 42. A computer only understands zeros and ones. So the compiler is able, or the compiler, the language, it knows how to take that 42, convert it into binary, and then it also knows how to load that binary value, that binary representation, into a particular memory location, keeping track that that memory location is associated with the variable a. Right? All of that is completely opaque to us. We never see any of that stuff happening because that's taken care of by the compiler, by the linker, by the operating system, etc. It's all below us. We don't have to worry about it. Again, it's the whole point of designing higher level programming languages so that we don't have to worry about those lower level details. Right? But with an object, with a user-defined object, the compiler / language does not necessarily know how to build it. Right? Or another way of putting this is to construct it. Right? And so consequently, we have to provide constructors, which is what you did in your lab this week. You had to provide a constructor to specify how this object gets, I think it's a book, is it? Or what was it? Yeah, it was a book or something, where you had to specify how this book gets constructed. Given its title, that title is assigned to that variable over there. Given its author, that variable is assigned to that thing over there, right? Et cetera, et cetera. So you have to specify how to construct it. Now, at the end of the day, the construction still relies on those lower level primitive types, that int, double, et cetera. All those things that are built in, once you use those as building blocks to define a constructor, a higher level constructor for your objects, right? All right, so i.e. you define and use constructors, right? And again, that's going to be a little bit different in other programming languages, right? General approach to object design is just simply that, quote, semantics dictate design. Design, there we go. All right. So what I mean by that is, before I give you an example, let's think of an example. Think about a bank account, because that's what I'm going to do later. What's in a bank account? In fact, let me jump over to Java immediately, and let's go ahead and create a new class. I don't know, bank account. Spell it right? Good. All right. What belongs to a bank account? What is a bank account? This is not Java now. I'm just asking general questions, right? I am asking, what are the semantics of a bank account? When I say a bank account, what do you mean? What do I mean? Right? It's like a savings account, right? And what constitutes a savings account? A what? Okay, so a balance, right? Right. What else? Account number. A way to uniquely identify it so that when I want to deposit it in my account. Whoa, what do you mean by your account? Right? If you're ambiguous like that, okay, I'll go ahead and deposit it in some random bank account. No, you need an ID, right? What else? Say what? Sorry, speak up. Like what? Like a name, like my awesome savings account or something, right? You can name accounts usually. I want to keep it simple though. Oh yeah, go ahead. All right, type like checking, savings, IRA, etc. Right? What else? Let's think about a savings account for one. You put stuff into a savings account. Why? Interest rate, right? And I'm going to call that an APR. Generally, we will leave this as APR for now. Generally, you want to avoid abbreviations unless they're very, very well understood. APR, I would argue, is in the context of a bank account. If you know what you're doing, you know what an APR is. But if I put in APY, maybe not. If I put in, ZYXT, right, then that might not be universal. And so I probably want to avoid abbreviations like that. Okay, this is pretty good for a first start. I mean, this is these are the semantics of an object, of a bank account. You just start thinking about a real-world object, and you start breaking it down into smaller and smaller pieces. Right? One piece that I do want to put here, though, is another piece. Whose bank account is this? I don't know. All bank accounts are mine, sorry. Right. That's a good design. I love that design. Right. I guess not if they're overdrawn. Right? So maybe an owner. Right. I'll go ahead and leave that. Now to simplify it, I'll go ahead and take out type for now. But let's start thinking about these things. Again, semantics dictate design. I want an identifier. Okay. Well, then when I go to design this, what should the identifier be? ID. ID is another abbreviation, but that's fine because everybody knows that ID is short for identifier. If you wanted to go with account number, maybe that's even better, right? Except the problem with most account numbers is that they're not really numbers, right? Account ID is what I'll put. So what type should this be? Are all accounts integers? No. So it could be what instead? Your account number is AA520, right? An alphanumeric designation instead. So what should I make this? A string. Okay. What about balance? Say what? Okay. Double is good. Float is only going to have 8 digits of precision. I guess a typical FDIC savings account is you lose up to 250,000. You can put more into it, but then it's no longer secured. And so that's going to be that right there alone, $250,000. That's going to be 6 plus 2, so that's going to be 8 digits of precision. I definitely want to think of at least a double. In practice, if you were doing a real financial application, the answer is neither one of those things. The answer is to use some built-in currency type that has multi-precision support. Because if you add a very large amount of money together with a very small amount of money, then you'll have round-off errors like many of you probably experienced in your first homework or in the first semester. And you don't want that to happen with financial applications. If you do allow bugs like that to happen, then you've got office space where you can steal a penny here from 50,000 accounts. You can steal a penny, and now you've got a good once a day for a year, and now you've got millions of dollars, and maybe nobody notices because nobody's going to report a penny missing from their account, right? You don't want to do that. So you want to use in some built-in type like a currency or something with multi-precision support where you don't lose that precision. Okay, but for this exercise, it's perfectly fine. A double. What about an APR? 5%. Is that an integer? Percent is probably a double. Okay, oops. Home row, there we go. Now, here's a good question. What about owner? Hold on to that for a second. What is an owner? A first name, okay. Oh, okay, first name, owner, first name. And, okay, well, we'll also want an owner last name. And we'll also want, I don't know, owner social security number. We'll also want string owner address. Oh, wait, what is an address? An address is a street number, city, state, zip. So, not address, address. What do we call the first line of an address? Street, thank you. String, owner, address, city, string, owner, address, state. Okay, I'm not even going to continue here. You see where the path that I'm going down here, right? I've got several different things here. Several different things that correspond to the real world. I've got an owner. What is an owner? Well, in the real world, an owner is a person, right? And what is an address? An address is 5 things, right? A street, city, state, zip, etc. If you find yourself breaking multiple objects and putting them into one object, you're doing what's called the God pattern, right? So yes, this is the God. It's called the God anti-pattern, I should say. It's a bad habit to get into, because I've not separated out the constituent components here. I've made this class into God. It knows everything. It sees everything. It does everything, and I don't want that. I want to split it out. What is this class called? It's called bank account. It should be doing bank account things, not street address things, right? So what I'm going to do is I'm going to separate this out into a person. Now I've got a person. Well, what did we say defines a person? Well, say these 3 things. They've got, and now I don't need to call them owner, because I called this person, not owner. A person can also be a prospective customer, and they're not an owner of the bank account. They could be a cosigner to a checking account, right? They could be an actual bank teller or a bank representative. I want to keep this general, so this is just a person. Every person has a first name. Most people have a first name. Most people have a last name. Most people have a social security number, right? And What else do most people have? They have an address. So let's go back over here and, okay, the address, street, city, state, zip. All right, let's bring that over here. I've gone down the same path again. What is this class called? Person. Does an address have a direct connection to a person? No. This should be this class should be responsible for person things, not address things. So let me again make another object, class address. Right? And I'll move that stuff over here instead. And instead of calling it owner address street, I'll call it street, owner address city. And I just want to draw your attention here to the difference. Right? If I'm naming my variables this thing, this thing, this thing, this thing, there are 4 things there, right? The owner's addresses state. There are 3 objects there. There's an owner, right? That's a person. There is an address. That's a different thing. And then the address has associated with it a state, right? So in the name itself, it is telling you the semantics dictate design. When I name something what it is, that name has a meaning. That meaning is telling you something. That this is an owner, it is the state of the address of the owner. And so there's a perfect opportunity for you to split those out into other objects. Right? City, state, what else do I need? City, state, zip. I'll leave it like that for now. Right? So address. Now coming over here, you no longer have those things. Instead you have, not a string, but what is an address? Well, I've got a class now to address that address. Right? Now this is all address stuff is now in the address class. It's all encapsulated in that class. Over here, the person class has everything to deal with the person. And over here, the bank account, once I get rid of all this stuff, is a person is the owner. There we go. Now, is there any address stuff in here at all? No. Implicitly, there is. If I follow the owner, right, and let me write public bank account, right, and just as a constructor, so I've got some access to this. Owner dot address first name. I could get their first name, or I can get their address. Right? And the address dot city, now I can get that. But it's semantically different. It's no longer just one big giant name that's meaningless to me. It's just a string. Right? Now it has a relation that this is the city of the address of the owner. Okay? There. This is called composition. A bank account is composed of a string, 2 doubles, and another class called person. Person is composed of 3 strings and another class called address. And actually, what is a string? A string is a class. So we are already using composition. We just didn't call it composition. And an address is the end state of this, where it only has 4 objects here. It's actually still composed of objects. If I go ahead and click on this string, I'm taken to, well, what is this? The string class is a class. It's another object. So you have object owning object owning object. Right? Whatever makes sense for what you're trying to model. Okay. So again, the general approach, if I approach and construct, I misspelled constructors too, constructors. There we go. The general approach is that semantics dictate design. Think about a real world object, break it down into parts until either you've broken it down to a piece of data that already has a representation, say a string, right? Or it makes sense to create a new class, right? And then you might break that down. That's the approach that I just did, right? The approach I just did was I thought about a bank account, and then I listed out everything that a bank account consists of. And I thought, oh, wait a second, an owner, that's several things right there. So I'm going to make another way of representing a person, and that has several things. Oh, it has an address. And I'll break that down into several things until I get down to the end, and there's really no way to break down a zip code anymore. And I guess technically there is. There are several parts to zip codes, right? Don't worry about that though, right? That's overkill. That's over-engineering, right? Generally, you want to use composition, where one object is composed of potentially multiple other objects, right? You want to avoid the God anti-pattern. Anti-pattern, there we go. Not everything should be in a class, right? Separate things out when it makes sense, right? A class should not know everything, see everything, or do everything, right? It should not be omniscient. It should not be omnipresent. It should not be omnipotent, right? Break things down. Avoid the God pattern. Now, for your first assignment, we kind of expected the God pattern, especially for the third one where you were doing the game report. A lot of people wanted to go, in fact, there was a question on Piazza that made us change the grader because of it. A lot of people wanted to break it down and start composing it of objects already, a game object, a publisher object, a platform object, and then tie those things together. It was a natural inclination. Great, right? And that should be your natural inclination because, again, object-oriented programming is a progression, an evolution of programming. We want to get over here to natural languages. We don't want to think like computers. We want to think like humans. And that's good if you try to do that, right? We weren't expecting it. We thought everybody would do everything in terms of strings, but it's very good. Right? It shows that object-oriented programming is a natural inclination for people when they want to, reason about a program. All right. All right. So that's objects. Now we need to talk about the 4 pillars. Sometimes people say that there are 5 pillars, and the fifth pillar, the first pillar that they're talking about is objects. But of course, if you're in a building, you have 4 pillars, right? You might have many, many more pillars, but you need at least 4 to hold up a square building. So it makes it nicer to just think about the 4 pillars instead. Those are abstraction, encapsulation, sulation, and inheritance, and polymorphism. And again, so far we've implicitly talked about the first 2. So those are going to be pretty quick that we're going to go through here. Abstraction, in fact, let's talk about abstraction in the context of, say, last semester. So here's my question. How does, and this will be Java, say, math.sqrt work? All right. So do you remember the answer to this question? How does the math library compute a square root? Nobody remembers the answer? Remember, be snarky. How many people are interested? Anybody? All right. Oh, okay. A couple of you want to get into numerical analysis. All right, that's good. I'll give you the answer. It's probably some numerical interpolation method or something, right? But not a lot of hands, right? You don't care, do you? Who doesn't care? Come on, yeah. Why don't you care? Because that's not the problem you're solving, right? Presumably, you are using square root to compute a distance or something, or you're using square root to compute a hypotenuse using the Pythagorean theorem, right? You're trying to solve a geometric problem. You don't care how square roots work, all right? You just want to use them. That is procedural abstraction. Procedural abstraction is how does a function, say like sqrt, work? Who cares? Right? We just want to use it. Right? The actual details of a function are encapsulated inside the function, so we don't have to worry about it. Now, I did call it encapsulation here. I used the word encapsulation. you'll find that abstraction and encapsulation are kind of like the yin and yang, right? They're kind of distinct, but they work together to accomplish something, right? And so you'll find that the abstraction peanut butter gets stuck in the abstraction chocolate, and yeah, it tastes great, right? Chocolate and peanut butter together. Sometimes you won't care what the difference is because they work with each other. They work with each other in order to accomplish some concept. So I am using the term encapsulation here because when we write a function like square root, we take that numerical interpolation method, that code, that algorithm, we put it inside the function, we wrap it up as a function, and then we don't care anymore, right? We just know that, oh, okay, it works, I'm going to use it. Input in, output out, right? I don't have to worry about the details. Now, if that is your problem, right, and you want a faster or more accurate method, then you do need to crack this egg open and start looking at the details and maybe modifying the details yourself. But that's usually not the case. Usually people don't write their own square root functions, right? They don't want to have to worry about those low-level details. Sometimes you do have to worry about them. But from the perspective of OOP, abstraction also deals with state. Right? And so here's my example. I'm going to go back over to the code here, and I'm going to rethink about a person. So a person has a first name, a last name, and a social security number, but they also have this is classically what we do, they also have a birth date. There we go. So what is a birth date? Again, let's go through that semantics dictate design kind of process. A date is a year, a day, and a month, right? It's not so simple. Which calendar? The Gregorian calendar, the Caesarean calendar, right? Chinese calendar. Many other cultures have different the Japanese calendar based on who's the emperor at the time, right? Mostly we're talking about the universal Gregorian calendar, right? Where you've got today is 2019, it is the first month, January, and it is the 31st, right? So let's break that up, right? Birth date, year, right? That's a number, right? Int, birth date, month, and I'm not even going to bother finishing. That's an integer too. But what are the problems with that representation immediately? An integer can be negative or 0. Was there a year 0? No, there wasn't. There was 1 BC and then became 1 AD, right, or CE. There was no year 0. So we've got a way to represent an invalid date. Negative values, that we might have an interpretation there, like negative 500, that could be interpreted as 500 BC or BCE. What about the month? What's the first month? 1? January, okay. Right. Anybody want to argue otherwise? What's another possibility? In computer science, we like to start our counting at what? 0. So you could go 0 through 11 instead, right? So already we're seeing that there is a mismatch here. Let's think about birth date from another perspective. Remember that semantics dictate design. You break a real-world object or idea up into smaller and smaller parts until you get to a part that's so small that you can just implement it. An integer, sure. A string, sure. Or maybe there's something already built into the language that'll do the job for you, like local date. And I do have to import it. So remember way back, not way back, but remember back to Lab 1. We had you bring in an external library called JOTA-DATETIME so that you didn't have to worry about the details of computing how many days are there from this date to this date. The library did it for you. And one of the ways that it represents dates is through this local date. It has to go with local date because, well, we're a large globe here, and on one half of it it's one day, and on the other half it's another day, right? And so we have to have a local date. What day is it where we are right now running this program? Now, the question is, how does it work? How does Java's local date work? Right? So some options here is it could have a collection of integer values, right? For a year, date, month. All right. What's another way that you can represent dates, though? Text. So it could represent it. It could be, and we have an ISO for that. ISO 1036. I don't know, or 1086, I think it is. Date, time, ISO. That 8601. I was very close. 8601 with these date time formats, right? 8601 formatted string, right? What's another way that you can represent date times or just dates? How does Unix do it? Second since the Unix epoch. All right. The Unix epoch was, let's go with this one. The Unix epoch was January 1st, 1970. It counts up the number of milliseconds since that date. Right now, and you can see the counter going up here by, that seems really slow. I wonder if those are like full seconds there. Yeah, timestamp to human date would be, there we go. So 0 would be January 1st, 1970 at 12 a.m. Right? There's already ambiguities too. 12 a.m., is that midnight? Or like if you're exactly at 12, which day are you? Right? It's right in the middle of yesterday and today, right? So which one is it? Who knows? Usually that's why your due dates are not at midnight. They're due 1 second before midnight, because there's always going to be an ambiguity there, right? That's another way of representing date times, right? So it could be a number, right? Say seconds from the Unix epoch, right? So I want to go back to my question. How does local date time work? How does it represent dates? What should your answer be? Who cares? Who cares? Right? The point of defining objects is abstraction. Right? You don't have to worry about the representation details. Right? You only have to worry about, and in fact, if you take a look at local date, it's got all of these methods that you can interact with it. If I've got a date, I can add 10 days by calling a method called plus days and passing it in 10. And then that date, then it'll return a new date that is 10 days later from that date. I can subtract 10 days and go back 10 days. I can add 50 years to this date, right? How is it working? Is it adding 50 to that integer, right? In the first representation? Is it using some ISO 8601 magic to determine how many, like it pulls out that one record for 2019 and then treats it as an integer, adds 50 to it, and then puts it back into that string? Or is it adding, 50 years times however many milliseconds there are in a year, and then adding it to that number? Who cares, right? Those are the details that are encapsulated inside of your object. Abstraction means that we don't have to worry about those details, right? It's a form. Sometimes it's referred to as information hiding, that it's hiding all the details that you don't have to worry about. I just want, what was I trying to do here? I just wanted a birth date, right? I don't want to have to worry about those time details and all the baggage that comes with it, right? So again, we've got that semantics dictating design kind of approach working for us. I don't want to know how to add 50 days to something. I'm just going to use what's built in. Now, if it's my job to build a time library, then I need to start worrying about those details. But once you've built the library and you've published it and it's bug-free, you've tested the library, it's bug-free, hopefully, then everybody is just a consumer of that thing. Just like you don't have to worry about converting that 42 into binary, putting it into a register, and worrying about the association of the variable a with that 42. Don't worry about those details. All right. Let's see. Usually I also give you another example. How does string work? All right. There are lots of ways of representing a string. In C, we represent a string as a character array with a null terminator at the end. We didn't cover PHP because we've changed the class a little bit, but how does PHP represent a string? It represents it as a character array, but without a null terminating character. How does SQL represent a string? They call them varchars. Typically, at least what I've seen, is they have basically an array of characters, but then the size of that array is prepended to it so that you know how many characters are in there, rather than relying on a null terminating character. How does Java do it? What's your answer? Who cares, right? Right? The details are encapsulated and abstracted away from us. Right? All we need to worry about now in Java is if I've got a string and I want to append another string, I just use the plus and I'm done. Right? That's actually a form of polymorphism that we'll talk about later. Right? And the next one, encapsulation. Right? And for this one, I'm going to talk a little bit more about the details of how it's done in Java. Remember that encapsulation consists of three things. It's the grouping of data. Hopefully this works. There we go. The protection of data and the grouping of methods that act on that data. Right? So for the first one, that's pretty obvious. All you need to do, is, like we just did, you break down an object and, okay, well, it has these things. Then you go ahead and put those things and you put them into an object, just like you did with a structure last semester, or you do in any language that has pieces of data that are related to each other. If you want to represent a person in the first name, last name, social security number, et cetera, you don't want to have to treat each one of these pieces of data as a separate variable. Ultimately, they are separate variables, but you want a way to group them together. Most programming languages allow you to do that in some way, whether or not it's through structures in C or some other programming languages, or classes or objects, whatever you want to call them. But Java has the protection of data, right? Visibility keywords in Java. Right? For example, you have, I don't want to go in that far, there we go. You have public. Right? This means that anyone can see, or not anyone, any piece of code can see the member variable or method. Right? You also have protected. Right? This will come back when we start talking about inheritance, but any subclass of the class can see the member variable or method. Right? And you also have private, which is only the class and instances of the class can see it. Right? And you also have in between there, I never remember where to put it, like if it's where I'm putting it or if it should be between public and protected. I forget, but there is what's called package protected. And you'll note that I'm not putting that in code because it's a lack of a keyword. The lack of a keyword makes the variable or the member visible to anything in the same package. Right? There we go. The demonstration that I just did, I didn't put any one of those keywords there. That makes all these things package protected. That means that if I look at the address, right, and I've got, say, here's public foo, right? And I'll go ahead and create a variable here called person, p, right? P dot, I can get their first name, right? I'm in a completely different class here, but I'm able to do to see it. Equals hello. There we go. I am in the, yeah, okay. Public void foo, that's what's the problem. I can see in this other class here, I can see that first name of the person class because we're in the same package. We're in the unl.csv package. Anything in this package can look at anybody else's stuff in that package. And that's what package protected means. If I go back over to the person class and do what I should have been doing, there we go. Oh, nope. There we go. And made everything private, now it can no longer be seen by address over here. It's complaining, right? And we did a demonstration like this a couple weeks ago. But now we have the idea of package protected, okay? It's very, very uncommon to see that. Usually, you make everything private unless you absolutely have to, right? So best practice, as we've said before, make all of your member variables private, vet, and control access through constructors and getters or setters. I need a better keyboard. Constructors. There we go. All right. But the third one is what I want to focus on now. Best practice dictates you should never separate the behavior of an object with its state, right? So what I mean by that is, let's go back to the bank account example over here, right? And we'll forget about address for now. Let me go ahead and get rid of this. Let's go over to the bank account. Now, we've got an APR and we've got a balance. One thing that we might want to know about this class is how much money are we going to earn in a year? Right? If I've got $1,000 in a bank account that's giving me 5%, how much money am I going to earn at the end of the year? So let's go ahead and make a method for that. Public double get annual earnings. Right? There we go. What should this look like? Does anybody know how to compute annual interest? It's not just simply 5% times 1,000, you get $5. Why? It's compounded every month. So 5% divided by 12, whatever that is, I can't do that. Let's say 6% divided by 12. Now that's 0.5%, right? Times $1,000. That's what you earn in the first month. That's added to your balance so that the next month, whatever that is, $1,000.50, now you're earning interest on that balance instead. How do you compute? So it compounds, and then the interest that you earn in the second month gets added to the balance, and now you're earning interest on a larger balance. And you do that throughout the year, right? This is basic finance. So how much do you actually earn by the end of the year? Because you're going to earn not $5 on 5%, you're going to earn $5 and some additional pennies, right? So the way that you do this is through what's called APY, right? Annual percentage yield. So APY is equal to, and here I never remember the formula, but it's going to be APR divided by 12 raised to 12, right? If it's compounded, this is if it's compounded on a monthly basis. If it's compounded daily, then you're looking at a credit card, right? Credit cards compound daily. Why? Because then they get more money out of you. Because if it compounds more often, then that means that the interest that you end up paying goes into your account, and now the bank is earning more money on your balance instead of you earning money on your balance. So that we'll go with monthly here, and this is APY. So how do I compute this? Well, it's just going to be simply the return balance times the APY, which is going to be 1 plus APR, or this dot APR divided by 12, raised to the 12th. Of course, I can't do that, minus 1. Right? So what we're going to have to do instead, math.pow, right? And then this 12, there we go. Right? And then I need to multiply this by putting that there and that there. Oh, okay, good. Right? We can make a really quick ad hoc test here. Public static void main string args. Let me go ahead and make a bank account. Bank account B is equal to, how do I construct a bank account? New bank account? Right? But the problem here is that now I'm going to have to set everything myself. B dot balance is equal to what, say $1,000. B dot APR is equal to 5%, 0.05. And then let's go ahead and system.out.println b dot get annual earnings. How much did I actually earn? I didn't earn $5. I will end up earning $5. Oh no, 5% of $1,000 is what? $50, of course, and some additional change here. Right? So that's how you can compute, say, annual interest. Now look at the design here, though. Forget about this testing for a second. Look at that design, and I'm going to get rid of this as well. Where is that behavior? Where is the we call it business logic, right? The logic that you need to actually implement your business rules. And in this case, it's the annual interest that you earn on a bank account. Where does that belong? Inside the class, right? Here is a way that you break encapsulation. Let me create a completely separate, different class called bank utils or something. Bank utils. Right? Now, given a bank account, we can go ahead and have the same logic. What is it? Let me go ahead and cut and paste this. Public, static, double. And what we'll do, we no longer, note that we no longer have this. There is no object here because there is no bank account. So we'll go ahead and put in a bank account up here. Bank account B. Right? And then I could go b.apr times b.balance, right? And I'll return that. Same exact logic, right? But a completely different design. Right? The function, the method, is inside the class in this instance. And in this instance, it's a static method that belongs to a completely different class. Right? Now, there's nothing inherently wrong with this. If you were doing something in C, which is procedural, this is exactly what I would expect because you don't have functions inside of classes in C. But now that you're in object-oriented programming, you should no longer think like this. You should think like this. Because I've got a class here called bank account. It's responsible for bank account stuff. One of the bank account stuff is computing annual earnings. Right? And a good encapsulation is putting bank account stuff in the bank account class. Bad encapsulation is putting bank account stuff in some other class. Right? In fact, I called it bank utils, so it's somewhat related. But if I just called it foo, right, that would be even worse. Foo is responsible for foo things, not bank account things. Right? So start thinking more in an object-oriented programming paradigm. Right? That if you've got stuff that acts on that data, and by acting on that data, I mean it is taking the balance and multiplying it by this formula and with the APR involved. It is acting on the APR and acting on the balance. It belongs inside the class because it acts on data inside the class. By ripping it out of the class here, I'm forcing it, basically I'm taking, the paradigm here is that I've got a bank account and then I rip it open, pull the two things out that I want, balance and APR, do my computation, and then send it on. Right? I am breaking encapsulation. That APR and that balance, they were encapsulated inside the class. I rip it open to pull them out. That's not good design. That's breaking encapsulation. Anytime you find yourself ripping an object open in order to work with it, you're probably doing it wrong. Right? So I'll go ahead and cut and paste these later. Okay. Best practice is, of course, to keep everything private. Objects also, I'll keep it like that. Let's see. Okay. So in sum, here's the key idea. Again, it's the yin and the yang, the peanut butter and the chocolate, or if you're familiar with Escher, MC Escher? Is it MC? What is it? Somebody help me. MC Escher? Okay. Well, he's not a rapper. But that's why I was thinking that's got to be wrong. But MC Escher, you know his famous painting of the two hands where one hand is drawing the other, right? Because one is the creator of the other. It's a paradox, right? That they are complementary because they created each other. Well, the key idea with encapsulation and abstraction is that they work together. Abstraction and encapsulation often work together, right? Abstraction allows access to an object's behavior, and encapsulation hides the details. Right? So again, it gets kind of mucky on where you draw the line. This is definitely an abstraction. This is definitely encapsulation, because usually they work in conjunction with each other. Okay. Inheritance. Oops, sorry, there we go. So questions so far? We do have about 10 minutes here, and so I will talk about inheritance, because when we get back on Tuesday, we really need to hit inheritance hard, because that's going to be on Lab 5. Right? But before I go on, I do want to give you a clear demarcation here. Right? We do not expect any inheritance or polymorphism in phase 2 that you're working on right now due next Friday. We are only expecting good abstraction and encapsulation in phase 2. Right? You are just creating data objects that are data containers. You don't even have behavior necessarily yet, unless you really want to go that far for the first phase. We are only expecting you to design your objects and then have minimal interaction with them. The interaction, of course, so hopefully you've all read it, is that you load up CSV files, you create instances of your objects, and then you dump them to another data format, JSON or XML or both if you're looking for that bonus. Right? The other thing that I would remind you of that I put on Piazza is that if you want that other extra credit of providing test cases that we'll actually use in the grader, we've already got dozens and dozens of test cases. We'll add yours to the library of test cases that we have, and when we do that, when you run the grader, I think you're given 5 randomized test cases. So if you give us those test cases to build that test case library, that's worth bonus, but it has to be done before Friday tomorrow, or before midnight tomorrow. All right? So keep those in mind. But otherwise, here's the demarcation. This is everything that we've talked about up till now. That's for assignment 2. Everything that we're talking about from inheritance on, that'll be it for assignment 3, where we expect inheritance and polymorphism to be used in your project. Okay. All right. Inheritance allows the extension of an object's behavior usually through subclassing. Right? Basically, in Java, you use the extends keyword to create a subclass. Right? The subclass inherits all the behavior, all the state and behavior of its, well, if we call one subclass, then what should we call the one above it? Superclass, okay. Superclass. One word or two? Yeah, okay, one word. Provided it is not private. Right? If it's private, then the subclass can't see it. So you can still protect it from the outside world by making it protected, right? That's why we call it protection. Right? And we'll see an example here in a second. In fact, unfortunately, the stock example that I'm not going to use is birds. So think of an ostrich, and I'll talk about it because it makes sense and it's very easy to understand. Think about a robin and think about an ostrich. They're both what? Birds. But they're also different, right? I want to call your attention to how they move. How does a robin move? It flies, right? Can an ostrich fly? No. An ostrich actually runs. They're quite fast, right? But they're also very, very tasty. If you do you have a Fuddruckers in Lincoln? I'm not sure. No? All right, just go up to Fuddruckers in Omaha and you can have yourself an ostrich burger. They're very good, right? They're cultivated. They're not captured wildly. But sorry if you're not a meat eater, right? But anyway, what I'm going to look at is a different type of account. So somebody already pointed out that, well, there are different types of accounts. Maybe we want to capture that. There's a savings account. There's a checking account. There's an IRA. There's a certificate of deposit account. I hesitated to put that down as a string because I wanted to do it in a different way. I wanted to do it in an object-oriented programming way. We might have a bank account. Instead of a bank account, what could I call this? What I was doing was I was building a savings account, right? And so I'm going to refactor this now, and I'm going to make this into a, rename this to savings account. There we go. Now I'm going to create another class called a checking account. There we go. Now a checking account still has what? What's in common with a savings account? Probably has an account ID, right? Probably has a balance. Probably has an owner, right? But an APR, well, lots of checking accounts offer you to earn interest. Even the best checking accounts that I've seen, though, are terrible. They're not even worth it. They just take everything in the back door through fees. So let's say that we're going to design this such that a checking account doesn't have an APR. You're not earning interest. But you might be paying a fee instead. Double monthly fee. Right? Now, if you do have a checking account that charges you a monthly fee, shop around, please. Go to a reputable local credit union. Don't bank with, like, say, Bank of America or somebody. They're gonna screw you somehow, right? So usually local credit unions don't do that. Right? They have a much better reputation. But let's just say that we're building this bank, and yeah, okay, we've got monthly fees. All right? I'm going to go ahead and close everything else here. And what I'm going to do is I'm going to show you another tool in your IDE. Here's my checking account. Here's my savings account. I've highlighted both of those by simply just holding down the command button and clicking both of them. On Windows, it would probably be Control, right? Control, click, click. I'm going to right-click, and you can look at Compare With. Let's see, where is it? Compare With each other. That opens up this nice little diff window, right? Where I've got a checking account on the left-hand side and savings account on the right-hand side. All of the differences are highlighted with this, like, slightly gray. I don't know if it shows up on the overboard here. And forget about the get annual earnings here. In fact, well, we don't have to forget about it. Public double get annual earnings. What do you earn from a checking account? Nothing. So we can have that there, right? So, but look at the number of lines that are different, and look at the number of lines that are the same. Which one's more? They're more similar than they are dissimilar, right? In fact, the commonalities here are the account ID, balance, and owner, right? And if I started doing more, if I had like getters and setters and constructors, I haven't gone through that exercise because we've done that before. I'd encourage you to do it on your own, though. And all it is just a button click with your IDE. But you'd see a lot more similarities, right? And if this were a more complex object rather than just a toy example to do in a lecture, then you would see many, many more similarities and dissimilarities. Remember the DRY principle from last semester. What does the DRY principle stand for? Don't repeat yourself, right? And in the context of CSE 155, that meant that if you've got this chunk of code and it's cut and paste it here and cut and paste it here, that's a huge red flag. Take that chunk of code and put it into a function. You've got the same thing, but in a different context here. I've repeated myself. I've got an object that has an account ID, a balance, and an owner. That's repetition. And if you've got repetition, then we need to eliminate that repetition, or we want to eliminate that repetition. To do that, I'm going to define a third class. New class. I'll call it bank account. Right? That's what it was originally. Right? And a bank account is going to have those things that are in common. Not the APR, but the three other things, or the monthly fee. There. Right? And I'll go ahead and take the opportunity here to make them all private. Or, no, I'm going to leave it there because we'll come back to it. And now, let me go ahead and, I'll leave this open. A savings account. You've got commonality with a bank account and a savings account in that these three pieces of state are the same. Semantically, again, semantics is meaning, a savings account is a bank account, right? But is a bank account necessarily a savings account? No, because we've got other types of accounts. Think back to that bird example. An ostrich is a bird. A robin is a bird. But is a bird necessarily a robin? No. So we've got kind of a hierarchy in our minds here. Up at the top, we've got the most general thing that we can think of, a bird. And down here, we've got specific kinds of birds. We've got a parent-child relationship. We've got a superclass and a subclass relationship. That down here, a subclass is an instance of the superclass. A robin is a bird, but a bird is not necessarily a robin. Likewise, with accounts, a savings account is a bank account. So I'm going to design it that way. Extends bank account. There we go. Now, a bank account has these three things. A savings account also has those three things. So we don't need them here anymore. All we need is the difference, the APR. Because we extend bank account, we inherit these things. Like I said, we had a parent-child relationship. When a parent dies, what does a child get? No, their inheritance, right? And so we are inheriting these things from the bank account, right? The savings account has a balance, right? I don't see a balance up here anymore, do you? Well, where is it coming from? If I click on it, where does it take me? It takes me to the superclass, bank account. Likewise, checking account. Let me go ahead and get rid of the redundancies there. And say that it extends bank account. Oops, one word. There we go. And spell it correctly. There we go. All right, there. Now let me go back to my comparison. What happened to all those things that were different? They're all gone. I've adhered to the DRY principle. Don't repeat yourself. Object-oriented programming achieves this through inheritance. If you've got common objects, you can take their similarities and promote them up to a superclass. If you've got differences, you can keep them down here in the subclasses. And we do have differences here. One has an APR that pays you. One has monthly fees that you pay the bank, right? And so we've got our differences down here in the subclasses, our commonalities up here in the superclass, so that it can inherit all those things. I don't need to repeat those three things. Now think about extensibility, right? The whole purpose of inheritance is for extensibility, that I want to extend the design of my system. I want to extend the design of this bank. I've only got savings accounts and checking accounts. Well, what else do I have in a real bank? I have certificates of deposit. I have, I think that they're old, but it used to be that everybody had a Christmas account, right? Where the idea was that you had a separate savings account that you squirreled away for Christmas, and then you pulled it all out to pay for Christmas presents or something. You can have a certificate of deposit. You can have a money market account, right? These are all different types of accounts that a bank uses. But do I have to go, when I want to design a new one, this new money market account, do I have to go back to square one and say, okay, well, this money market account, obviously it has an owner, it has an ID, it has, what else do we do? It has a balance, right? No, all I need to do is create a new class that extends something that I've already built. I want that functionality. I don't repeat that functionality. I extend that functionality, and now I inherit all the work that I put into that superclass. Right? That's the advantage of inheritance, and that's the power of inheritance. We will go over it in more detail when we come back on Tuesday, and then of course you'll do it in Lab 5 in the context of Java. Okay.